Okay, let's dive right into this, because there is a massive, fundamental paradox right at the heart of toxicology education. I mean, think about it for a second. To become an expert in hazardous substances, to learn how to identify toxins, and ultimately save lives, you literally have to study poisons. And that inherently puts students in danger. Imagine being the professor responsible for a room full of 19-year-olds handling lethal chemicals. It's a nightmare, right? How do you safely study something whose entire defining characteristic is that it's completely unsafe?
Well, welcome to The Explainer. Today we are breaking down a really fascinating piece of educational technology that is completely solving the inherent dangers of the science lab. We're looking at how immersive 3D toxicology virtual labs are allowing students to master complex, highly hazardous scientific methods without ever being exposed to a single harmful substance.
Here's our quick roadmap for this explainer. First, traditional hazards. Second, the virtual solution. Third, branches of toxicology. Fourth, overcoming limitations. And finally, number 5, the top 5 simulations.
Let's start with Section 1, Traditional Hazards, the Physical Lab.
You know, toxicology isn't like sitting in a history or mathematics lecture. It fundamentally involves getting your hands dirty with hazardous chemicals, biological hazards, and incredibly risky laboratory procedures. Imagine the immense stress of trying to maintain safety standards when a single spilled beaker could mean exposing an entire classroom to something truly dangerous. It's an unbelievably difficult environment for universities to manage safely, let alone cost-effectively.
Moving right along to Section 2, the virtual solution, risk-free learning.
So, what exactly is a toxicology virtual lab? Basically, it's an immersive, 3D computer-based environment. It's meticulously designed to help students learn fundamental scientific methods and practical lab skills, but completely without the real-world hazards of toxic materials and organisms. Think of it as a 100% risk-free sandbox for serious, rigorous scientific experimentation.
And going virtual absolutely doesn't mean watering down the education. In fact, students still hit all their core learning goals. They're actively identifying the effects of toxic substances on cells and organs, and analyzing complex dose-response relationships. They develop essential observation and recording skills, and crucially, they improve their confidence through repeated practice, which is something you can rarely do in a physical lab without wasting thousands of dollars in chemicals. All of this happens without the lingering anxiety of a real-world spill.
All right, Section 3, branches of toxicology, medical to forensic.
We can group the healthcare branches together to start. Over in medical and clinical toxicology, students are learning how to diagnose poisoning and manage toxic exposure cases in healthcare settings. Then in pharmaceutical toxicology, the focus shifts to evaluating drug safety, analyzing side effects, and testing toxicity during the development of new drugs. Virtual labs provide the absolute perfect arena for students to train for these high-stakes roles. And keep in mind, these are the people who might one day treat you in an emergency room, so we want their training to be flawless.
But toxicology goes way beyond the hospital. Contrast the medical side with these sectors. Environmental toxicology looks at how pollutants impact entire ecosystems. Industrial toxicology examines workplace chemical exposure risks. Forensic toxicology is straight out of a true crime podcast, literally investigating poisons in criminal cases. Then you've got food and chemical toxicology, looking at contaminants in our diets and the hazards of industrial chemicals. The software is versatile enough to cover all these incredibly diverse fields in one platform.
Which brings us to Section 4, overcoming limitations, physical versus virtual.
Physical labs are completely plagued by high costs for chemicals and equipment, massive material waste, and very limited access, because obviously you can't just leave a toxic lab unmonitored. Virtual labs powerfully flip that script. They offer zero material waste. They grant 24/7 remote access so students can learn from their couch at 2 in the morning if they want. It's a risk-free environment that allows for unlimited repetition, completely removing the financial and physical barriers to learning.
Now you might be thinking, but wait, do they still learn how to be safe in a real lab? It's a common misconception that virtual labs skip over real-world safety. As our source material highlights, the software specifically simulates proper laboratory safety protocols and emergency responses. Students are actively forced to practice safe chemical management virtually, learning how to handle fumes and biological hazards long before they ever step foot into a physical facility.
Let's get to the really fun stuff. Section 5, Top 5 Simulations, Virtual Experiments. Our first featured simulation is the in vitro mammalian chromosomal aberration test. That's a mouthful, but it is a highly advanced experiment aimed at detecting structural chromosomal aberrations.
Essentially, students are hunting for different classes of DNA damage during cell division, and they do this using a virtual light microscope. Just look at the rigorous steps a student has to execute here. First, they check the confluence and count cells under the microscope, then dilute them for a 24-well plate. Next, they actually have to calculate and prepare the chemical doses. They treat the cells with genotoxic agents or nanoparticles. Then comes harvesting, fixing, and staining with gene-stain. Finally, they analyze the cells using the virtual light microscope and interpret the resulting data graphically using dot plots. They aren't just clicking next, they're executing precise, realistic, scientific procedures step by step. And the software doesn't stop there. Students can also dive into an LDH assay to measure cell damage, an acid phosphates assay to quantify enzyme activity on living cells, or even evaluate the genotoxic effects of nanomaterials using a cytokinesis block micronucleus assay. And that brings us to the fifth key simulation we're highlighting today, the XTT viability assay. This simulation tests the viability of cultured cells right after they've been exposed to geometric concentrations of different nanoparticles.
What I absolutely love about this is how beautifully it grounds the software in reality. The student has to aspirate the old medium and add the new chemicals. They add the XTT solution and incubate the cells, but then they have to read the results using a virtual microplate reader to calculate the viability percentage, exactly like they would use a physical microplate reader in a real-world lab. It's incredibly hands-on, even when it's totally digital.
Now here's a kind of surprising real-world fact to pull this all together. Do you know what the most common toxicology test actually is out there in the real world? It's the urine toxicology screening test. Why? Because it's quick, non-invasive, and highly cost-effective. Physical labs often have to rely on simple tests like this just because of tight budgets and safety constraints. But virtual labs? They allow students to run highly complex, repeatable cellular assays, like those chromosomal aberration tests we just looked at, without ever worrying about the cost of materials or the danger of the chemicals. Which leaves us with this final provocative thought. If a toxicology student can now run complex, highly hazardous chromosomal and nanoparticle assays hundreds of times in a risk-free, zero-cost digital environment, what limits of scientific discovery are we removing? By democratizing access and completely eliminating the physical dangers of the lab, how much faster will the next generation of scientists be able to push the boundaries of medicine and environmental safety? It's a massive shift in how we learn, and it's happening right now. Thanks for tuning into this explainer.